Now let's see some definitions, some results, and then we will go for singular integral equation. Remember, we are now studying about the symmetric integral equations. Okay, so let's see some definitions. Symmetric kernel. Symmetric kernel k x comma t is said to be 1. These definitions you already came across in the linear algebra. Non-negative definites. Bilinear forms, they are non-negative definite if inner product of k phi with phi is greater than or equals to 0 for all phi. In fact, you might have came across about these definitions in your course of functional analysis too. Okay, so I'm just recalling that definitions here. Second, this is called positive definite. Positive definite if inner product of k phi with phi is always greater than or equals to 0 for all phi, and inner product of k phi with phi is equals to 0 implies this phi has to be equals to 0. Then it's called positive definite. It cannot be 0 here in this case. If phi is not equals to 0, then this has to be a positive quantity. Third, so non-negative nowadays becomes non-positive definite. Make the ulta non-positive definite if inner product of k phi with phi is less than or equals to 0 for all phi. Fourth, out of this there is negative definite if same inner product of k phi with phi is less than or equal to 0 for all phi, and inner product of k phi with phi is equal to 0 implies phi is equal to 0. So 1, 2, 3, 4, and fifth, it is called quasi-definite when all but a finite number of eigenvalues are of one sign. Now understand the meaning of this. The quasi-definite when all but finite number of eigenvalues are of one sign. Okay, understand the meaning of this. And it is called symmetric kernel kx comma t is said to be indefinite if it is not the type mentioned above. And this is how we classify symmetric kernels. Now based on this, let's see some examples and then we'll check the complete things. Right, so result, let me just put two results here and then we can try by yourself. Result, let me put first here a non-null means non equals to 0, non-null symmetric kernel kx comma t is non-negative definite if and only if all its eigenvalues are positive. This will prove, and let me put the second one for you. Non-null symmetric kernel, kx comma t is positive definite if and only if there are 2 points here. If all its eigenvalues are positive and the second point is eigenfunctions forms orthonormal system. Of course, you know what is orthonormal system. Let us try to prove this first one here. Second one we can try prove first one. So let k phi equals to integral from a to b. This is the notation what we are using from long kx comma t by t dt. So if we have k phi like this, then by Hilbert-Schmidt theorem, what we have is k phi or fx is equals to k phi. Yeah, in this case, in Hilbert-Schmidt theorem, we use fx is equals to k phi. So k phi is equals to summation n from 1 to infinity fn phi n of x. Okay, this is nothing but fx. This is equals to summation n from 1 to infinity. Fn is phi n upon lambda n, fn upon lambda n, and this is phi n of x. There is a difference between this phi n and this phi n of x. Be careful. This is the function. This is the quantity number. Okay. So this is equals to summation n from 1 to infinity. Phi n is nothing but phi with phi n, in the product of phi with phi n divided by this lambda n is there, and then we'll have here phi n of x. So take the inner product of this with phi, we'll get, this implies inner product of k phi with phi will be equals to, you can take that inner product inside, summation n from 1 to infinity, inner product of phi with phi n upon lambda n, this is the number, we can take it outside the inner product, properties of inner product, and then we'll have inner product of phi n of x with phi. Okay, now remember this thing. Now let's take the conditions. If lambda n is greater than 0 for all n, then inner product of k phi with phi will be greater than or equal to 0, because this is norm of phi n of l double square, and this is positive, and this entire thing will be depending on lambda n. So if lambda n is greater than 0, then the summation will be greater than 0, and since it's an infinite series, it can be 0 also. So this is this is done. Now if lambda n is negative for some n, counter positive for some n, then let us take the inner product of k phi n with phi n. Then inner product of k phi n with phi n will be equals to same. In place of phi, you take phi n. This is summation n from 1 to infinity. Inner product of phi n with phi n, in place of phi to phi n upon lambda n, inner product of phi n with phi n, and this will be equals to 1 upon lambda n. So summation n from 1 to infinity, phi n with phi n, phi n with phi n, those are the orthonormal sets. Otherwise all are 0, then this becomes 1 upon lambda n, and since lambda is less than 0, 1 upon lambda n will be less than 0, and then we are done. Right? So this completes our proof of result 1, which is if and only if statement. Now using this kind of things, let's just state a theorem called Mercers theorem. Let's take the Mercers theorem. MERCERS, Mercers theorem. Use a simple. If a non-null symmetric L2 kernel is quasi-definite, definitions are already given, quasi-definite, and is continuous, then the series summation n from 1 to infinity 1 upon lambda n, this is a series for your eigenvalues, is convergent. And not only that, and the kernel kxt x comma t, which is given by summation n from 1 to infinity phi n of x, phi n of t bar upon lambda n, the series, this is the infinite series, the series being uniformly and absolutely convergent. We will not go in the proof of this theorem, but let's write one remark based on this theorem. Mercers theorem gives condition to extend these bilinear forms, in this case the kernel, the bilinear form, say k x comma t, to infinite series which is uniformly and absolutely convergent. So this Mercers theorem gives the condition. This is a bilinear form which is absolutely, we are writing this kernel kxt as a infinite series which is uniformly and absolutely convergent. Okay. Now let's go for one of the result and we will wind up with this topic and we will go for the singular integrals. So the result, we will prove these results. I will give the proof of this result too. Result for a real symmetric kernel k x comma t with infinite number of eigenvalues. The following are equivalent. One means if one holds then two will hold, and if two holds then one will hold. Right? One, integral from a to b k x comma t psi t dt equals to 0 for all x belonging to a comma b. If this happens, then let me write 2. Integral from a to b ij of t psi t dt will be equals to 0 for all j from 1 to 2 and so on. Since this has infinite number of eigenvalues, it will be an infinite number of eigenfunctions. Now this for this psi belongs to L2 class, and this phi j are eigenfunctions of kxt. This implies this phi is the eigenfunction of kxt means I'll just write this. This is phi j is equals to k phi j, and then the eigenvalue is here. Okay, so we have to assume 1 and show that 2 holds, and we have to assume 2 and show that 1 holds. So let me give a proof 2. Proof. Suppose 1 holds. Suppose 1 holds. So that is 1 holds means what? It is integral from a to b k x comma t psi t dt is equals to 0 for all x in your domain. Because you are integrating with respect to t here. So if you take any x from the domain a comma b, then this integral equals to 0. That's what your assumption is. Now, in order to get 2, you multiply by phi j of x and integrate from a to b. So already it is integrated with respect to t. Now you are multiplying by phi j of x and you are integrating with respect to x. So be careful when you write. So integral from a to b phi j of x, and then this integral is already there. Integral from a to b k x comma t psi of t dt dx equals to 0. Now change the order of integration. This implies integral from a to b. You change the order of integration. This order is nothing but from dt and dx, and you make it dx dt with the conditions. You check the conditions where you can change the order of the integration, or you can check what is the procedure to change the order of the integration. Okay, so change the order of integration. This becomes psi of t dt, and this is integral from a to b kxt ax comma t phi j of x dx dt equals to 0. Now remember, our kernel is symmetric kernel, and this is nothing but lambda k phi j. If you take this as lambda k phi j, you can take this lambda down other side, and this will be phi j upon lambda. Okay, so this becomes, this implies that lambda will take out this entire bracket. This thing is nothing but phi j upon lambda. So this is integral from a to b phi of t, and this is phi j of t upon lambda dt equals to 0, and this happens for j from 1 to n, so on. Now this implies lambda is not equals to 0. Uh, this implies what we have to do is the second one. That's almost done. It's done. Integral from a to b phi j of t phi of t dt will be equal to 0. And we have taken phi j. We can take phi 1, phi 2, anything. So this will happen for j from 1 to n, so on. So we have assumed that one holds, and we have proved that the second condition also holds. Conversely, conversely, let integral from a to b phi j of t psi of t dt is equals to 0 for j equals to 1 to n, so on. Now for that we have the truncated kernel. Check the definition of truncated kernel now again. So we have truncated kernel t n plus 1 x comma t given by k n plus 1 of x comma t is equals to, this is the definition of the truncated kernel, minus summation j from 1 to n phi j of t phi j bar of x upon lambda j. So if you rearrange, this implies our kernel kxt becomes this k n plus 1 of x comma t, and we are shifting it this side. So plus summation j from 1 to n phi j of t phi j bar of x upon lambda j. So when you multiply this equation by side and take the integral from a to b, so this implies, on next page, this implies integral from a to b k x comma t multiplied by psi of t dt. This will be equals to integral from a to b the truncated kernel k n plus 1 of x comma t psi of t dt, plus you can take that integral inside the summation, and that becomes summation j from 1 to n 1 upon lambda j is constant, you can take it outside the integral. Phi j bar of x is independent of variable of integration, a to b phi j of t psi of t dt. And we assume that integral from a to b phi j of t psi of t dt equals to 0. So all the terms from this summation will be 0, and this implies integral from a to b k x comma t psi of t dt is equals to integral from a to b the truncated kernel k n plus 1 x comma t psi of t dt, and this all the terms from this equals to 0 because of the assumption this becomes 0. So when you take the norm, this implies norm of integral from a to b k x comma t psi of t dt will be equals to, this is nothing but norm of, this is nothing but k n plus 1 of psi. So this is norm of k n plus 1 of psi. This is less than equals to summation by functional, this is k n plus 1 operators and psi, norm of psi. And this tends to 0, these are the truncated kernels, so this tends to 0 as n tends to infinity. So if this tends to 0 as n tends to infinity and this is inside the norm, this becomes, or this means, this implies the integrand, I mean that x in the norm will go to 0 as n tends to infinity, and since it's a norm, it will be greater than or equal to 0, and this implies integral from kx comma t psi of t dt will be equals to 0, and this is what we wanted to prove. So these are some results, and let me wind up this topic by giving a note and by studying another result. So note, a symmetric kernel, is called complete if relation 1 implies psi of t is equal to 0. It is called closed. It is also called closed. It is also called closed. Now relation 1 means this. So if integral from a to b kx is at it equals to 0 implies psi of t is equals to 0, then this is called a closed or a complete kernel. Okay. Now note that by using this, note that equation 2 implies orthonormal system phi j is complete. And let me just put up a result and we'll stop here. Result: symmetric kernel is complete if and only if system of its eigenvalues, eigenfunctions is complete. So in the next video we will see some theory from the singular integrals and how to solve the singular integrals.